So we've added vectors and we've multiplied vectors by scalars. So now we're going to multiply a matrix and a vector. So we have a couple of examples here. The first thing you have to check to see is if the dimensions match up. So the matrix on the left has 2 rows and 3 columns. And the vector, which is really a matrix with only 1 column, it has 3 rows and 1 column. So to be able to multiply these, the number of columns of your matrix on the left has to equal the number of rows or the number of entries in your vector. So those two have to be equal, and they are here. And the result that you get will be the outside portions. So our product is going to be a 2 by 1 vector. So here's what you do. You take each entry in your vector and you multiply it as a scalar times each corresponding column of the matrix. So I will multiply the first entry of the vector times the first column of the matrix, and then I'm going to add the second entry in the matrix or in the vector times the second column of the matrix, and then the third entry in the vector times the third column in the matrix. You see it's like you create a linear combination of the columns of A and you use the vector as the weights or the scalars. Right? And if we simplify all this, let me just multiply the scalars inside first. So I get 4, 0, 6, negative 15, and negative 7, 21. And now we're just going to add those up. And you see you're going to get a 2 by 1 vector from this. It's like 3 and 6. So our product here is the 2 by 1 vector, 3, 6. Now that seems kind of weird. You've multiplied a 2 by 3 matrix times a 3 by 1 vector, and we get a 2 by 1 vector. But that's how we've defined matrix multiplication, and there's a good reason for it, and we'll get to that. But let's just do another example here. First, we're going to check to see if the dimensions match. This is a 3 by 2 matrix. This is a 2 by 1 vector, and these match. The two columns match the 2 entries of the vector. You know, you're taking these entries and multiplying it times these columns, so there has to be the same number of those to be able to do that, right? The number of those things have to match up. So this is 4 times the first column plus 7 times the second column. And let me just simplify this. So that's going to be 8, 32, negative 20, and negative 21, 0, and 14. We add those together. I get negative 13, 32, and negative 6. So let's take this equation here. This is a linear combination, a vector equation, right? And let's write it as a matrix times a vector. So 3, negative 5, 7 are the coefficients or the weights of the linear combination. And V1, V2, and V3 are actually vectors. You see they're bolded here. You know, they're not using my vector notation, but these are vectors. So the vectors are the columns of our matrix. So this would be our matrix. And then our vector will be the weights. So that's it. That's a matrix times a vector. Now we don't know what v1, v2, and v3 are, so we don't know what the matrix looks like, but we know that those are the columns. And this says write a system of equations as a matrix equation. So let's look at this and see if I say, well, I've got a 0x1 in this second equation, right? Because I don't have an x1 term. And I look at this as 1 and 0 are both being multiplied by x1. I can say, well, this is very similar to x1 times the vector 1, 0. And this x2 is being multiplied by 2, negative 5. So that looks like it's x2 times 2, negative 5. And we have x3 times negative 1, 3. Which is equal to 4, 1. We'll just write those as vectors. This would be called a vector equation. But this is weight x1 times this column, and weight x2 times this column, and weight x3 times this column. So this is the same as this matrix times this vector equals 4, 1, the vector 4, 1. So this would be called a matrix equation, and now maybe you'll see why do we multiply matrices and vectors this way. Is because it matches up with how our systems look, right? So we've got 3 different versions of a system. So we have just the system, we have a vector equation, and we have a matrix equation, and they all represent the same thing, right? They're all talking about the same exact situation. And sometimes we would just call this matrix A, and we would call this vector the vector X that has these components, and we would call this guy over here B, and we get this kind of standard form of what a matrix equation is. It's going to be a matrix A times a vector X equals a vector B. And that multiplication, this A times X, is that funny multiplication that we did with the first examples. So the matrix system, the matrix equation AX equals B, has a solution if and only if B is a linear combination of the columns of A. Meaning, if B is a linear combination, and that's what this left side is, right? It's a linear combination of these vectors, and those vectors are the columns of this A, then that's saying this guy only has solutions if this has solutions, right? If B can be written as a linear combination of the columns of A. So it's just connecting these two ideas together, this vector equation and this matrix equation. We say that they're equivalent systems, right? This only has a solution if the vector equation only has a solution, and that's another way of saying B is a linear combination of the columns of A. So that leads us to a theorem here. If A is an n by n matrix, then the following statements are equivalent. Now, when we say equivalent, we mean if one of these is true, then they're all true. And if one of these is false, then they're all false, because they're all really the same thing. Okay, they're just different ways to say the same thing. So number one, for every vector B in Rm, AX equals B has a solution. So if AX equals B has a solution, for every B in Rm, then for every B in Rm, that can be written as a linear combination of the columns of A. So that's what we just said a minute ago, right? But that implies the next two. That means the columns of A have to span Rm. So that means if you span the columns of A, you get every vector in Rm. So let's go back. This is a linear combination of the columns of A, right? If I took every possible linear combination of those, and I got every single R2 vector, then every single R2 vector that I plug in for B, I'm going to get a solution, right? Because every B can be written as a linear combination of those columns. Okay, and then that also means that A has a pivot position in every row. So if you have a pivot position in every row, you can't get a row of zeros, right? You can get a free variable, so you could get infinitely many solutions, but you can't get a no solution because you can't get a whole row of zeros in A and then B on the right side be something that's non-zero. So if A has a pivot position in every row, then every B can be written as a linear combination of the columns of A. The columns of A span Rm, and for every vector in Rm, Ax equals B has a solution. If you just reduce A and you get a pivot in every row, then it doesn't matter what the right side is, you're always going to get a solution there. And that means you can always write B as a linear combination of those columns. So let's go back to this guy. So I skipped this one, but I think we can answer this easier now. Let A be this matrix and B be any R3 vector. Is Ax equal B consistent for all possible B's? Well, we don't know what B is, right? B can be anything, but I can row reduce A. And if I get a pivot in every row, then the answer is yes. I'm always going to get a solution no matter what the B vector is. So let me put this matrix in my calculator. I'm cheating here using the calculator. Check it real quick. It's like I messed up the very first row. Okay, so you always check because I messed that up and I had to fix it. So RREF, the matrix A. And I do not get a pivot in every row. Let me convert that to fractions. So A row reduces to this matrix. So the answer is no, since A does not have a pivot in every row. So that you could find a B that when you did all these row reductions, the third entry would be non-zero, and you would have a no solution system.